The Koch snowflake is a mathematical curve and one of the earliest fractal curves to have been described. It is based on the Koch curve, which appeared in a 1904 paper titled On a Continuous Curve Without Tangents, Constructible from Elementary Geometry by the Swedish mathematician Helge von Koch. Construction. The Koch snowflake can be constructed by starting with an equilateral triangle, then recursively altering each line segment as follows. Divide the line segment into 3 segments of equal length. Draw an equilateral triangle that has the middle segment from step 1 as its base and points outward. Remove the line segment that is the base of the triangle from step 2. After one iteration of this process, the resulting shape is the outline of a hexagram. The Koch snowflake is the limit approached as the above steps are followed over and over again. The Koch curve originally described by Koch is constructed with only one of the 3 sides of the original triangle. In other words, 3 Koch curves make a Koch snowflake. Properties. Perimeter of the Koch snowflake equals, after each iteration, the number of sides of the Koch snowflake increases by a factor of 4, so the number of sides after n iterations is given by. If the original equilateral triangle has sides of length s, the length of each side of the snowflake after n iterations is. The perimeter of the snowflake after n iterations is. The Koch curve has an infinite length because the total length of the curve increases by 1/3 with each iteration. Each iteration creates 4 times as many line segments as in the previous iteration, with the length of each one being 1/3 the length of the segments in the previous stage. Hence the length of the curve after n iterations will be n times the original triangle perimeter, which is unbounded as n tends to infinity. Limits of area and perimeter. As the number of iterations tends to infinity, the limit of the perimeter is. Since a dimensional measure exists, but has not been calculated so far. Only upper and lower bounds have been invented. Area of the Koch snowflake equals, in each iteration a new triangle is added on each side of the previous iteration, so the number of new triangles added in iteration n is. The area of each new triangle added in an iteration is 1/9 of the area of each triangle added in the previous iteration, so the area of each triangle added in iteration n is. Where AO is the area of the original triangle. The total new area added in iteration n is therefore. The total area of the snowflake after n iterations is. Collapsing the geometric sum gives. Limits of area, the limit of the area is. Since. So the area of the Koch snowflake is 8/5 of the area of the original triangle. Expressed in terms of the side length s of the original triangle this is. Other properties equals. The fractal dimension of the Koch curve is log4/log3 per mil 1.26186. This is greater than the dimension of a line but less than Peano's space-filling curve. The Koch curve is continuous everywhere but differentiable nowhere. Tessellation of the plane. It is possible to tessellate the plane by copies of Koch snowflakes in 2 different sizes. However, such a tessellation is not possible using only snowflakes of one size. Since each Koch snowflake in the tessellation can be subdivided into 7 smaller snowflakes of 2 different sizes, it is also possible to find tessellations that use more than 2 sizes at once. Few more sequence and turtle graphics. A turtle graphic is the curve that is generated if an automaton is programmed with a sequence. If the 3 or more sequence members are used in order to select program states, if t, n, equals 0. Move ahead by 1 unit, if t, n, equals 1, rotate counterclockwise by an angle of I/3, the resulting curve converges to the Koch snowflake. Representation as Lindenmayer system, the Koch curve can be expressed by a rewrite system. Alphabet, f, constants, plus, a, axiom, f++f++f, production rules, f of phi f++ phi f, here, f means draw forward, plus means turn right 60 a degree, and a means turn left 60 a degree. Variants of the Koch curve. Following von Koch's concept, several variants of the Koch curve were designed, considering right angles, other angles, circles and polyhedra and their extensions to higher dimensions, squares can be used to generate similar fractal curves. Starting with a unit square and adding to each side at each iteration a square with dimension 1/3 of the squares in the previous iteration, it can be shown that both the length of the perimeter and the total area are determined by geometric progressions. The progression for the area converges to 2 while the progression for the perimeter diverges to infinity, so as in the case of the Koch snowflake, we have a finite area bounded by an infinite fractal curve. The resulting area fills a square with the same center as the original, but twice the area, and rotated by I/4 radians, the perimeter touching but never overlapping itself. The total area covered at the nth iteration is, while the total length of the perimeter is, which approaches infinity as n increases. See also, List of fractals by Hausdorff dimension, Gabriel's horn, Flosnake, self-similarity, Weierstrass function. References: Edward Kistner and James Newman, Mathematics and the Imagination, Dover Press, reprint of Simon & Schuster, ISBN 0-486-41703-4, pages 344 €51. External links: CPW Fed Koch Snowflake Fractal Antenna for UWB Wireless Applications, Von Koch Curve, The Koch Snowflake in Math World, The Koch Curve Poem by Brent Wall, Computing Iterations of the Koch Curve in Wolfram Alpha, Application of the Koch Curve to an Antenna, a WebGL animation showing the construction of the Koch surface, a mathematical analysis of the Koch curve and quadratic Koch curve. Retrieved November 22, 2011.